This is lesson 4.3 on tree diagrams and counting techniques, and this lesson covers how we are going to determine outcome totals and specific outcomes. Ordinarily, we work with probabilities that have equally likely outcomes. So throwing a dice, tossing a coin, the outcomes have the same probability of happening depending on what we throw. When that's the case, then we're going to use the simple probability formula where the probability of event A is the outcomes favorable to event A over the total outcomes. Let's say, however, that we have different numbers of outcomes. So this is where the fundamental counting theorem comes in. This is also called the counting rule or the multiplication rule. So let's say you decide to open a breakfast shop next to Mingo Park during the summer months. You want to keep it simple, so you offer donuts, mini muffins, and pastries. The breakfast special is one of the above, a banana or an apple, and either coffee, milk, or hot chocolate. How many different combinations are there? So this is the counting rule. You have your main choice, your fruit, and your drinks, and each one of those is like its own event. Selection of the main choice comes from donuts, mini muffins, or pastries. Second event is a selection of fruit, the banana or the apple. And the third event is a selection of a drink, either coffee, milk, or hot chocolate. Now we're going to take each of those and we're going to multiply the number of outcomes together. So we get 3 times 2 times 3, and that is equal to 18. That's the number of possible outcomes. Now take a look at your notes. A sandwich shop offers 3 kinds of sandwiches: shredded chicken, Q beef, and tuna salad. And no, I don't know what Q beef is. Customers have their choice of buns or Kaiser rolls and may have either chips or apple slices on the side. So each of these lunch specials has a choice of sandwich, bread, or sides. You have 3 different kinds of sandwiches, you have 2 different kinds of breads, and you have 2 different kinds of sides. So your total number of combinations is going to be 12. Now, let's say that you wanted to know how many specific kinds of lunches you have. All right, in order to get the specific ones, you have to go ahead and do a tree diagram, because the counting rule only gives you the total number of outcomes. It doesn't give you any specific outcomes. So the tree diagrams are set up by events. So the first event would be selecting one of the sandwiches. The second event would be selecting the bread, and the third event would be selecting the sides. So if we select the sandwiches, we're looking at the shredded chicken, the Q beef, and the tuna salad. Now, each one of those also comes with either the bun or the Kaiser roll. Okay, now each one of those comes with a choice of banana or potato chips or apple slices. Now, if we count up the final column, and you'll notice that we have 12. So that's also the number of outcomes. But if we wanted to know a specific outcome, for example, how many combos have a regular bun and chips on the side, we look for the regular bun and follow it to the right and see how many of those offer chips. So we have 1, and then we have in the middle another bun and another possibility with chips, and down at the bottom another bun and a possibility of chips. So 3 out of 12, or 1/4 of the combinations, have a regular bun and chips on the side. Now this is a standard tree diagram. It's not a real hard one to make. Some of them are a little bit more challenging. Okay, so take a look at your notes. It wouldn't be a probability chapter if there wasn't a bag of marbles somewhere, somehow. So we have a bag of marbles. It has 6 in it, 1 red, 2 blue, and 3 yellow. And we're going to use a tree diagram to find the probability of specific selections, taking 3 marbles out of the bag. So each event or each selection is our event. So our first event is the first selection. And we have a choice of either a red, yellow, or blue marble. Okay, the second selection is dependent on the first. So there was only one red marble in there. So in the second selection, if we picked a red one first, then our choices are blue and yellow. Now for the other two, we've got red, yellow, and blue. Okay, now for the third selection, if we started with a red and then a yellow, we still have yellow and blue. If we started with a red and a blue, we still have yellow and blue. In the second selection, if we started with yellow and then pulled out a red one, our choices are yellow and blue. If we started with a yellow and we pulled out a yellow one, well, we still have a yellow one, all the blue ones and the red ones. So we've got red, yellow, and blue. And the same is true for the yellow and then followed by a blue selection. Okay, when we get down to the blue, if we pulled out a red first, then all we have left is yellow and blue. If we pulled out a blue one and then a yellow one, we have red, yellow, and blue left. And if we pulled out a blue one and then a blue one, okay, now both of the blue ones are gone and our choices are red and yellow. If we did this again, if we kept going, and we could go about 6 times total because we have 6 marbles. Okay, if we went it started out with few possibilities and then they're gradually getting larger with more possibilities, but we're also running out of marbles, so eventually it's going to go back down again. However, if we wanted to know the probability of selecting a yellow marble followed by a yellow marble followed by a yellow marble, well, there's only one way we can do that out of all of these ways. And how many different ways are there? Well, if we count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So there's one way out of 19 that we can select a yellow marble 3 times in a row. The last part of this has to do with factorials, permutations, and combinations. So factorials are more than excited numbers, which you see the exclamation points. You can tell they're excited. And you're probably feeling a little excited too. I know I am. So actually that exclamation point is its own operation. So any number followed by an exclamation point is that number times 1 less than that, times 1 less than that, until it gets all the way down to 1. So example 1 is 3 factorial, which is 3 times 2 times 1 equals 6. Example 2 would be 5 times 4 times 3 times 2 times 1, which would be 120. Okay, so the nice thing about factorials is that they are embedded in your calculator. So if you can find a PRB button and select that, you should get an entire menu with the factorial, permutations, and combinations. If you do, then go ahead and clear out your calculator, select 5, then go to your probability menu, select the exclamation point, and then hit equals or enter, and you might have to hit it again, and you should get 120. Now, could we do this one in our head? Of course we can. But sometimes the numbers get bigger. Sometimes we get 10 factorial. Go ahead and try that one. Put in 10, then click the probability button, select the exclamation point, and click enter once or twice, whatever it takes. That is not a number that we want to do in our heads. Okay, also we use these factorials when we do permutations and combinations. So permutations are arrangements, okay? How many different ways can you arrange a certain number of items? So in example 3, how many ways can you take five items and arrange them 3 at a time? All right, well, wherever you found that exclamation point, you should have also seen an NPR. And so in order to do this one, we can either use the formula at the top, or you can put in the 5, click the probability menu and select NPR, and then put in a 3. And you should get 60. Let's try that again. With example 4, put in the 7, click the probability button, and then the 2, and hit equals, you should get 42. All right, combinations are the same thing, except that in this case, order doesn't matter. The order is not important. So in this case, you have an extra variable in the denominator, and that kind of takes out all the doubles. And so your combinations, the number of combinations are usually going to be smaller. Well, they're always going to be smaller than the permutation. So let's go ahead and use 5 and 3 again, but this time it's a combination. So put in the 5, find your probability menu, click NCR for combinations, and put in the 3, and hit equals. And this time you should get, let's see, 5. And you should get about 10, which is much smaller. For example 6, put in the 7, then NCR, and then put in the 2, and hit equals. And if you've done it correctly, you should get 21. All right, so that should explain everything that's on the notes and everything that you need to know for this set of exercises on page 170. If you have any questions, just let me know. Drop me an email and I will get back to you as quickly as I can. Thanks. See ya.